All right, by the way, that MATLAB project, remember, it's due on Monday, right, the last day of class. So please keep that in mind and try to do a fair job on it. And there's one signature item you have to put that your work is your own. It's a line on there, and it's important to do that too. Okay, so with S parameters. Now, I've used these, and there are all sorts of parameters that are similar to them. There are A, B, C, D parameters, there's H parameters. Do you remember when you had microelectronics, right? You had analog. Remember HFE, the gain of the transistor, forward gain, current gain, and stuff like this? All those parameters, H parameters, everything like that can be determined or can be gotten from the S parameters. But S parameters are the way they measure. Here's what it amounts to. We're going to start with a two-port network first. This is primarily in the microwave case, higher frequencies, but you can do it at lower frequency too. So we're going to have a device, and it's just showing us a black box. And it's going to be characterized by something called the S parameters. Here we're going to have a transmission line. It's going to have a characteristic of P and Z naught. And this will be port 1. Then we're going to have another, usually the transmission lines are the same Z naught. Another transmission line here, this is port 2. Let me just see. Get a marker that's got some real color. I think I've been down this road before. I think these markers. Well, I can try them for a second. Anyway, so at port 1, we envision a wave, two different waves. One's coming at the port. This is going to be a wave, and this will be called V1 plus. But one's going away from the port. This would be V1 minus. And again, it's a potential developed between the two parts of the transmission line, or waveguide. And it's going this way. Some is reflected, that would be V1 minus. Here in port 2, you're going to have a signal, an incoming signal. That would be V2 plus, and then you're going to have a reflected signal. V2 minus. Now remember, this is transmission line. So you've got waves coming in, some reflecting, waves coming in here, some reflecting. And the relationship is, it's through the S parameters, it's V1 minus is equal to S11 times V1 plus S12 times V2 plus, and V2 minus is equal to S21 times V1 plus S22 times V2 plus. The way it's usually written is like this. V1, V2 in a column vector is equal to, and then it's S11, S12, S22, 21, pardon me, and S22 times V1 plus, V2 plus. And sometimes it's just S with two bars over it and V with a single bar like this. It'll be V bar, or V, what you call it? V minus is equal to S double bar, V plus. But it doesn't matter how you write it. It always means the same thing. And if there were 3 ports, then you would have a V3, and you would have S31, S32, S33, and so forth. So now we talk about what this means. This is voltage. So if you look at this, when I take a look at V1 minus over V1 plus, that will be S11, assuming V2 plus is equal to 0. Let me try to explain this. If you take a look at this, if you have no signal coming into port 2, V2 plus is minus, then effectively what you have is a matched condition over here. There'll be some load that would have Z naught effectively. And any wave that comes out of here is going to be just dissipated into that. There's no reflected wave, no V2 plus. So this S11 right there is the reflection coefficient. It would be the reflection coefficient at port 1. assuming V2 plus is negative. You all follow me? And the way you do that is just put a match load condition on that. That way there can be no, I'm assuming there's no active generator here, but what happens sometimes is V2 minus comes out, hits something, reflects back, so you have V2 plus. Just keep that in mind. So that's the reflection coefficient. In a like manner, if we look at port 2, if we get V2 minus over V2 plus, that's equal to S22, assuming that V1 plus is 0, and that too is a reflection coefficient at port 2. By the very definition of reflection coefficient. Do y'all follow me on that, class? Nothing tricky about this, but I'm gonna apply it to several situations so you see it. Now, when we talk about these parameters S21 and S12, we're really talking about the voltage gain. And I'll put them over here. When you look at S21, if I take V or V2 minus over V1 plus, that is S21, and it's assuming that V2 plus is 0. And here's what I mean by that. If I look at this, S21, it would be V2 minus over V1 plus, assuming V2 plus is 0. You all follow me? That's called the forward voltage gain. Now, when you're doing in high frequency engineering, if you're using a standard bipolar transistors it's current controlled current amplifiers by definition, but when you put the resistors and stuff and load it, then you can get a voltage controlled voltage amplifier. Just try to appreciate that. Generally speaking, bipolar transistors are current controlled. FETs are, and this gets a little hairy because we talk about the DC bias of those things, but when you have FETs, they too are current controlled current amplifiers, but they can be viewed as voltage controlled voltage amplifiers. So don't worry about that too much. Remember, this is only going to determine the voltage amplification, not the current. This is important, just to appreciate it. So now we're going to apply this to some situations and see what happens. We're going to calculate the S parameters for some situations. Some of these are extreme, but at least the minute you start applying this, when you start figuring things out. So I'm going to do it over here. And what I'm going to do is what Wentworth does in his book. I'm going to take this model of circuit right here. And the only thing I'm going to do is short this terminal. All right? Y'all follow me on this? This is port 2. By shorting this terminal right here at port 2, what I effectively do is say that V2 plus V2 minus are equal to 0. Y'all follow me? Because when you have a port, anytime you have a transmission line or a waveguide, you have outgoing and incoming waves that superimpose at the point of the port. When you direct, and I'm trying to show you short right at the port here, not with any length to it, because if it was a little further away, then we have to change this. But if you look at this, right, V2 plus V2 minus is 0. It's a short circuit. Do y'all agree with that, class? That's the definition of a short circuit. There is no voltage crossing, which means the plus waveform would cancel the minus if it had any value. Now, in that case, when I come over here, let me do it this way. Come over here. That's still port 1, so I'll write that equation. I have V1 plus, V1 minus is equal to S11 V1 plus S12 V2 plus, and I have V2 minus is equal to S21 V1 plus S22 V2 plus. I made this condition V2 plus V2 minus equals 0, or really V2 minus, or V2, I should say V2 plus is equal to minus V2 minus. Y'all follow me? I just took it to the other side. So if I come over here, I take a look at V2 minus here, and I say that's equal to really minus V2 plus. I'm just looking at this. So I'm going to just say This V2 minus is really minus V2 plus. Y'all follow me what I'm doing here? I'm not trying to be tricky, I'm just showing you the necessary steps you take. Now, what I'm going to do, I want to get one equation with just V1 minus and V1 plus. Actually, what I want to get is reflection coefficient of port 1. I didn't say that clearly enough. I'm looking for just reflection coefficient of port 1. And the reflection coefficient of port 1 is V1 minus over V1 plus. That's the definition. All right. When I have reflection coefficient over here, V2 plus, that would be when this is actually preventing any signal from ricocheting back, then you get the reflection coefficient of that part. And it is, when that is the case, we get S11. Here, we're assuming we know the S parameters. So we're going to assume we know the S parameters, we just short the port when we want to get that reflection coefficient. I should have said that a little clearer to start with. All right, now take a look at this. Y'all follow me right here? Now what I'm going to do is I'm simply going to rearrange this. So I'm going to take this term to this side. So it's minus S21 V1 plus, and I take that term to that side. So I have 1 plus S22 times V2 plus. Y'all follow me? I'm just rearranging things. I want to get V2 plus by itself in terms of V1 plus. So now I take this and divide it by 1 plus S22, and now I get this. Can y'all follow me? I'm just rearranging. I want V2 plus because I see in here, if I replace this V2 plus in the first equation with this, I have everything in terms of V1, either minus or plus. So when I do that, and I'll do it right here, I've already made that condition. Then when I get this, I get V1 minus is equal to S11 V1 plus S12 times V2 plus, which is that, which means this becomes minus, and it's times S21, and it's over 1 plus S22, and this is V1 plus. This is just playing a little game of reorganize it, so I can get the definition. By definition, reflection coefficient is V1 minus over V1 plus, regardless of what port 2 is doing. That is the definition of the reflection coefficient of the port. So then I can say the reflection coefficient of port 1 right here would be equal. Now we divide by V1 plus. V1 minus over V1 plus is equal to simply S11 minus S12 S21 over 1 plus S22. This problem is in Dr. Wentworth's book. That's getting the reflection coefficient of the port. When you know the S parameters and you do something like a crazy termination like that. If you're asking me what use is it to do that, not really any use, except to show you how mathematically you calculate the reflection coefficient at that port. So that's the first example of S parameters being used. The next one, and this is the one you pay attention to because it really exemplifies some things you have to understand. Have you guys used S parameters ever before? In the lab or anything? Have you used HFE? Current gain? Remember that? Beta? Remember there's a beta DC? All right, beta is HFE, it's a forward gain, but it's a current gain. All those things are related to these S parameters. When you characterize a network, what you really do in high frequencies, and I've been involved in this several times, you're going to have whatever it is, an active amplifier or whatever, and you're going to have port 1 and port 2 that you'll have transmission lines driving, or at least being connected to, and you'll have something called a network analyzer. And you will measure the S parameters versus frequency, and you'll characterize the network over the operational frequencies. That's really important. That's the way all high frequency engineering, at least for amplifiers and filters, how it's done is with these network analyzers. Let me ask you this, have you ever been exposed? You know what a network analyzer is? You do? You got one head shaking, some heads. Have you used an oscilloscope? When you use an oscilloscope, you plot waveforms versus time usually, right? Voltage waveforms versus time. Have you used a spectrum analyzer? All right, that gives you the frequency spectrum of a voltage waveform. You all remember that? It takes snapshots in time and does a fast Fourier transform, gives it to you. A network analyzer is similar to a spectrum analyzer, but it will give you information about S parameters primarily over the frequency. So you'll basically drive a port and with a voltage, and you'll sweep the frequency, and you can extract the S parameters based on these conditions here. It's a little much, but spectrum is for 2-port measurements. Network is for 2-port. Spectrum is just one. So here's the classic that you should start with. I'll have a transmission line with characteristic Z0 equals 50 ohms. And then, for whatever reason, I'm going to just have a simple resistor, make it R equals 100 ohm here. Then I'm going to have my second port. This is going to be a transmission line with a characteristic impedance Z0 equal 50 ohm. And I want to characterize this. So this is my network right here. Kind of an odd network, it's a single resistor. Y'all follow me? Okay, now, when we look at this, we're going to go ahead and get the S parameters. The first parameter we're going to get is S11. And S11 is equal to V1 minus over V2, or V1 plus, assuming that V2 plus is 0. So here's port 1. Here's port 2. So, the first thing I do in my mind, this is a little mental experiment, thought experiment. I'm going to say, I'm going to terminate this thing to a 50 ohm load. And the reason I'm doing that, there will be no reflected waveform coming back into this port. So I know I can guarantee V2 plus is 0. You all follow me on that, class? If this thing wasn't 50 ohms, if it was 100 ohms, then there's a reflection coefficient here, and some of the signal that's transmitted through there would reflect back. Right, so I have to make sure, at least mentally, that that is 0. It's called a matched condition. So now I go ahead and I look at this, and I got my V1 plus mentally coming at this thing. And really, you know this from the past. Anytime you're talking about a reflection coefficient at this port, that's what this is. This is the reflection coefficient at that port, assuming that V2 plus is 0. What you're really talking about is the impedance you're looking at. When I look at this reflection coefficient, which is S11, which is the reflection coefficient of port 1, I'm looking at simply the Z right here that would be in, Z in that I see there, minus Z0, minus the impedance I came from, over Z in plus Z0. Y'all follow me? I want to make sure you think about this. Remember, when you talk about reflection coefficient, it's always the impedance you're going into minus the impedance you came from over the sum of the two. That's reflection. All right, what impedance do I see here? It's this simple. I have 100 ohms there for sure, and I have 50 ohms. So it's 150 ohms. Do y'all follow me? So the reflection coefficient of this thing is going to be 150 minus Z0, which is 50, over 200. Well, that reflection coefficient is going to be 100 over 200, or 1/2. It's that simple. So that would be S11. Does it make sense to you the way it's done? You got to get the impedance you're going into, and then you have to know the impedance you came from, and it's just simply impedance you're going into minus the impedance you came from over the sum of the two. So that's the reflection coefficient in port 1. By the way, how many people see this? If I want the reflection coefficient in port 2, as this network looks exactly the same. Just spin it around, right? It's a symmetric network. Do y'all see this? Wouldn't it be the same too? It would. When I look at S22, that's equal to reflection coefficient of port 2, which would be V2 minus over V2 plus, assuming V1 plus is 0, and just throw that matching condition over here, it will be the same, it will be exactly 1/2. He has the sinusoid. Now, after that, we're going to go ahead and get the actual forward voltage gain. Now, when you think about this, V2 minus over V1 plus is equal to S21, and that assumes that V2 plus is equal to 0. Do you all follow me on this, class? Now, I want you to think about this. This is the one that's tricky. I'll leave that up there. What I'm really doing is this. I'm saying I've got V1 plus coming in, and I want to see what comes out. That would be a voltage gain. Even if it's actually reduction, they use the term gain. I want to see what V2 plus is. Do y'all follow me? Now, here's how you do that. And I'll do it right over here. I have a voltage coming in here. I'll try to explain this to you. I have a voltage coming in here, V1 plus. There's going to be a certain amount of that voltage, call it V prime, that gets across the boundary. But some of the wave is actually reflected, and I'll get V1 minus. Do y'all follow me on that? So what I need to do is get the transmission coefficient right here. I need tau. And the transmission coefficient, you can get it by saying it's 1 plus the reflection coefficient, right? And in that case, or you can say it's 2 times the impedance you're going into over the impedance you're going into plus the impedance you came from. Either one of these two will do it. Well, for my case, I got a reflection coefficient of port 1 equal to 1/2. That means this, we can do it both ways, the actual transmission coefficient, which is the ratio of V prime over V1 plus, will be equal to 1 plus 1/2 is 3/2, and we can get it this way too. Our input impedance is equal to 150, right? On port 1, y'all follow me? We talked about it. So 2 times 150 is 300, right? 300, and then it'd be 150 plus 50 or 200, 3/2. It works out either way. Y'all follow? Okay, so now I can say that right here, when I look at that voltage, this voltage is going to be tau times V1 plus. And that would be the voltage just on the other side of this connection. Some of that wave's going to reflect back, but some of it right there is developed right across there, okay? Now, of that, now you've got a resistive bridge here. Can you see that? You've got 100 ohms in series with 50 ohms. So that means that voltage is going to be reduced, whatever this voltage is, the voltage developed here would be 50 over 50 plus 100 times this voltage. Do y'all follow? So I can say that V2 minus would be equal to tau, and then it's the voltage division of really 50 over 50 plus 100. So now I'm going to get, and that would be times V1 plus. So I get V2 minus equal to tau, which is 3/2 times, and this is going to be 1/3 times 1/3 times V1 plus, and therefore I can say that V2 minus over V1 plus will be equal to simply 1/2, and that would be S21. So let me go on. This would be the matrix so far. The S matrix for this is 1/2, 1/2. Those are the reflection coefficients, S11 and S22. Then for that, the forward gain is 1/2. This is an interesting network. Anybody want to take a guess what the reverse gain is? The reverse voltage gain? In other words, if I put a voltage V2 plus here, how much V1 minus comes out? You're right. It's a symmetric network. Can you all see that, class? It looks exactly the same either way you look at it. So this would be 1/2 also. This is a problem out of this book. It just gets you started. Everything's 1/2 there. but it's the beginnings of your understanding of S parameters. You have to at least have an appreciation for this to move on. So then, by the way, this is the problem in page 561. I made sure I did the exact problem. Don't worry about reciprocal networks, I'll just mention this. A reciprocal network is something where this is not a big deal. Reciprocal network, it's in the book. It's the next thing that he talks about. That's where S itself, the matrix, is simply equal to S transpose. Y'all know what transpose is on? You had linear algebra, right? You just shift these two parameters, right? Flip them and you get a transpose of matrix. Well, to me, it's nice. Okay, we can call it reciprocal. I call it a symmetric network. This is a reciprocal network. You look at it one way, it looks identical as looking at it the other way. There's nothing different about it. So you can flip it around. You can take port 1, make it port 2, make it port 1. It'll have the exact same properties. That's effectively reciprocal, or I call it symmetric. And either one, this is a definition, I guess, used by the industry. Now, then he talks about lossless networks next. If you want to know where I'm at, it's on page 563. And I'll mention this. This is not a big deal to me, but here's the rule of thumb. All right, when it says lossless network, what do you think about immediately? A lossless network is one. No power is lost, right? What loses power? Do capacitors lose power? Do inductors lose power? Do resistors lose power? Yes. So if you see a resistor in a network, it's not lossless. Y'all follow me? Now, if you don't know if it's lossless or not, but you measure the values of this you measure the S parameters, then you'll find out that if you take S, and here I gotta be careful about his terminology. He's gonna use transpose and conjugate. So if you take S transpose, there's other ways to do this, I'm certain. S transpose, and this is a multiplier, then you multiply it by S conjugate. You get what's called the unitary matrix. Now the only thing that means is the unitary matrix, that symbol there, regardless of how many port system, if it's 2 port, it's 1, 1, 0, 0. If it's 3 port, it's simply 1, 1, 1, and everything else 0. And he'll have that in his book. So if you multiply the transpose times the conjugate of the matrix, you're gonna see, if it's all ones on the diagonal, it's a unitary matrix, and if it's all ones, it's lossless. To me, that doesn't, I don't care. I really don't. I mean, when you measure these things, this might be important. I don't want to be flippant about that, but it may be important if you're measuring the performance of, say, an amplifier, and you want to see what level of loss it is. Maybe doing that operation is worth doing, but for anything I do, it doesn't matter to me. Once I have the S parameters, that's all I care about. Whether it's lossless or not, there's nothing actually is made it perfectly lossless, but some things have a high level of efficiency with very low loss. And anytime the network is just capacitors and inductors, it's about losses. The minute you see a resistor, it's not. All right, just keep that in mind. That's the easy way to do it. Okay. Next thing, we'll talk about return loss and insertion loss. And really, I don't want to spend too much time on this. Let me erase this. And this is really, it's just taking the log of the logarithm of certain quantities. So, if you have a system like so, port 1, port 2, and you talk about a return loss. I want you to think about this naturally. Return would be something, you send a signal in and it comes back. This would be V1 plus going in, this would be V1 minus coming out. So the return loss, or RL, return loss, is equal to minus 20 times the log of the magnitude. In his book, he uses the symbol, he uses the reflection coefficient here, reflection coefficient at the port. So the return loss for whatever port it is just equal to the reflection, 20 times the log, minus 20 times the log of the reflection coefficient. I want to mention something. The way it's usually, or the way I think about this, that reflection coefficient is S11, or it's S22, or it's S33. Y'all follow me? Assuming it's matched in almost all two-port networks, if you're using a three-port or N-port, you always want to have a matched condition. You want no reflected wave coming back at you. Right? That would be bad. So usually I just put S11 there. If I want the return loss of port 1, minus 20 times the log of S11. Return loss of port 2, minus 20 times the log of S22. Now, yeah, if there is some complication like that short circuit I showed you in the beginning, then you would have to get the true reflection coefficient with that short, and then you would have to take minus 20 times the log of that. But I don't really want to spend time on the odd situation. This is generally return loss for any port. And you might as well just make a little note here. This is SII. So it is a reflection coefficient, or it's the S parameter for that port, the reflection coefficient. Either 1, 2, 2, 3, 3, whatever. Now, when they talk about insertion loss, what you're always thinking about is if I put a signal in port 1, how much that signal gets out on port 2. Do y'all follow me? So, insertion loss, or IL, and they'll have I comma J here. That's really minus 20 times the log here. And I call it S, magnitude of S, and this would be I comma J. Let me explain to you. In his book, well, he actually doesn't do it that way. He wants to do it this way. I'm sorry, this is return loss. No, it is insertion loss. IL. And the way he does it is insertion loss for ports. And he's going to have I comma J is equal to minus 20 times the log of, and then he has VI minus over VJ plus. Here's what it amounts to, because I don't like to confuse you this way. If I want the insertion loss for really 2-1, that's simply minus 20 times the log of S21, assuming it's matched. Assuming that both ports are matched, right? So that would be the insertion loss for port 2-1, right? It's actually the insertion loss of the forward gain, the voltage gain. And S12 would be minus 20 times the log of the magnitude of S12. That would be the reverse. That'd be the insertion loss for the reverse voltage gain. Now, I don't worry that much about these two. This is pretty straightforward. If you want a loss, it's always minus 20 times the log of the magnitude of that S parameter, generally speaking. Return loss is always reflection. Insertion is always the gain. Always worry about the gain. Y'all follow me, class? And don't make a big deal about that. It's not worth it. All right. Now next he talks about a shift in the reference plane. And this gets a little interesting. Before we do that, I think we should do
I'll do that shift and reference plane in a second, but I wanted to do a few problems because doing problems makes this stuff a lot more clear. And in the book, let's go ahead and try some of these. I'm gonna erase this, and I'm gonna do a couple of these problems, because remember last time we did a bunch of problems that had to do with L section matching, and I think it really helps to see how they should be done. So I'm gonna do a few of these, but I wanna make sure that you follow me. If you have questions, ask. I'm trying to do this the way Whitworth's book does it, in the order. A lot of the stuff, it doesn't matter the order you present it, like reciprocal networks and lossless networks. That's, to me, not even important, but to him it is. So let's do this. If you have your books, you can follow along with me. So we're going to have a 50 ohm transmission line. We're going to do this. This is problem 1025. Got a transmission line that has 50 ohm. Cut it, and then you put a 50 ohm resistor in series, and you shunt it with a capacitor, and oh, I'm sorry, shunt 50 ohm resistor, not even a capacitor. This is just going to be a 50 ohm resistor. And then it's connected back to a transmission line with a characteristic impedance of 50 ohms. So he asks, is this network lossless? Anybody want to take a guess? Lossless?
Oh, no.
No, it's not lossless. Somebody asked that. Determine the scattering matrix for the 2-port. All right, so next we determine the scattering matrix. By one look you can tell. All right, so how do we get the scattering matrix? How would you get this? Let's get S11. So what do we need to get S11? This is port 1. This is port C. By the way, I put the solutions for chapter 10 up there. I don't know if you took a look for all the problems. They're there. All right, so I want S11. Now, I know you've just been introduced to this, but S11 is what? It's V1 minus over V1 plus, assuming what? V2 plus is 0, right? In other words, it's matched. So I'll just put this for the betterment of everybody. I'm going to put 50 ohms here. So in your mind, you know that nothing is reflected back into port 2. I'm just doing that for a mental thing. All right? So how do I get that? Well, what's the secret? I have to get this, right? I need to get the input impedance right there at port 1. Go with me? So what is going to be the input impedance Z in port 1? Now I want you to think about this logically. If I'm at port 1 and I'm looking in, I've got 50 ohms for sure, right? But then I have 50 ohms here, and it's in parallel with that transmission line, which is equivalent to a resistor that's 50 ohms, right? So if I have 50 in parallel with 50, 25, right? 25 and 50 is 75, right? So this is 75 ohms. So when I look at this, the input impedance there is 75, which means the reflection coefficient at port 1 would be what? The impedance I go into, 75, minus the impedance I came from, 50, over the sum of the two, which is going to be what? 125, is that right? Correct, class? And what's that going to be? Well, that's 25 over 125, right? Or it's 1/5. You all agree? So that would be S11, 1/5. All right. Now, take a look back. The next one I'm going to do is S22. I don't have to do this, but I'm going to. So S22 is V2 minus over V1, or V2 plus, pardon me. V2 minus over V2 plus with V1 plus being 0. So now I get rid of this just for mine. And I do this only because I'm trying to make sure you guys understand. I'm doing this so you know, in your mind, you know there's nothing coming out, hitting something, reflecting back. That'll happen later. But on these, they have to assume match. So here, I want this. So what do I need? I need this right here, don't I? Z in of port 2. You agree with me? I'll slow down a little. We're missing quite a few people. 2, 4, 6, 8, 10. 1, 2, 3. We're missing at least 3, maybe 4 people. I don't know if the others have dropped or not, but we're missing several people. 1, 2, 3, 4, 4. All right, so again, what would Z in here be? Just draw it up. This is port 2, right? We're looking in here. First thing we have is a 50 ohm right here, right? That's 50 ohm. And then what do you have? You got 50, right? And you got 50, don't you? This would be the transmission line. So what's the input impedance here?
It's 33.33.
I've got 50 in parallel with 100, or you're right, I think it's 33.33 ohms. Who said that? You did, you're right. I believe it is. 33.33 ohms, right? So now we come down here, and again, that first port's matched. So that's the impedance I'm going into, or it's 33.33 minus the impedance I came from, which is 50. That's this impedance over the sum of the two, right? 33.33 plus 50. Well, what's that going to be? It's negative, isn't it? Correct, class? It's got to be negative. 33 minus 50 has got a negative on it. What do you get?
Minus 0.2.
Yeah, that sounds right. But minus 0.2, or it's really minus 1/5. We actually did the numbers. All right, so it's minus 0.2 or minus 1/5. Something's odd here. 1/5 there, minus 1/5 there. Now we need the forward voltage gain. Now I want to get S21. That's equal to V2 minus over V1 plus, assuming V2 plus is 0, right? So now, mentally, we're going to do this. You don't have to do this. I'm doing it for your sakes. Now I'm going to put 50 on load here, so you know this thing's matched. So if I put a voltage waveform here, I'm going to take plus minus, and I'm going to have this V1 plus coming in. Now remember what happens here. The key is getting this voltage right here. I need that V prime. Y'all follow me? With me, class? So what's that going to be? Well, V prime would be the transmission coefficient at this port times V1 plus, correct? So I need the transmission coefficient at port 1. Let me do it here. What's the transmission coefficient at port 1 going to be? Well, 1 plus the reflection coefficient at port 1. Do you agree with that? What was the reflection coefficient? 1/5, right. So this is going to be 1 plus 1/5, or it's going to be really 6. That's 5/5 and 1/5 is 6/5, isn't it, class? All right. So that means my V prime that I showed you there is going to be tau 1 times V1 plus, or it's 6/5 V1 plus. That means that's what this voltage is, just on the other side of port 1's connected. Then I have this voltage division that happens. Take a moment. I've got 50 ohms, but it's in series with a parallel combination of 50 and 50. So, we do it up here. When I look at that, this is where my V prime is. And now I've got 50, and then the parallel combination of 50 and the transmission line 50 ohms is going to be 25. And what I really want is this voltage. I want this voltage right here. That would be V2 minus. Y'all follow me? So what's that going to be? V2 minus is going to be V prime, right? That's the voltage across this series combination, and then it's times simply 25 over 25 plus 50, or V2 minus is equal to V prime times, and this would be 1/3. Do you agree with that? I'm gonna stop and let you just grasp, just take it, think about it. Y'all, everybody agree? You good with me? All right. So what's that gonna be? Well, when I take a look at this, I can say V2 minus is going to be V prime is 6/5 times V1 plus times 1/3, right? Or it's really 2/5 times V1 plus is equal to V2 minus, and therefore, when I take V2 minus over V1 plus, it's simply 2/5. Does everybody agree with that? And again, the key to this thing is getting that voltage just on the other side of port 1's connection. It's either gonna be, some. Cockroaches, but if you can stomp on them, please do. We don't need cockroaches. We have enough problems. He's making a bolt for the door. Boom. Well, if you can, if somebody wants to, you're free to go stomp them. I'm not a fan of cockroaches. All right, anyway, y'all with me on this class so far? That's the first time I've ever had that. So it's 2/5. Let's do the last one we need. Now we've got 2 1s. So as far as the S parameters, let's put them up here. So far for S parameters for this network, we have what? S11 is 1/5, 1/5. S22 is minus 1/5, correct? And then S21, what did we get for that? 2/5. This is 2/5. Finally, we need S12. I'll put it up here and we'll do it. So when we talk about S12, that's equal to V1 minus pest control.
Get 'em one more time.
You know, they say after a nuclear war, there's 2 things that are gonna remain alive. You ever heard this? One of them is cockroaches. Do you know what the other one is? Keith Richards. Okay, so if we're doing this, now the situation changes and we look this way. Now we match this port, right, with 50 ohms. And now we're gonna put a signal here. This is just a thought experiment. So this is V2 plus coming in. And we want to get this. So guys, now you tell me what to do. I want to get S12. And think about what I really need. Got a wave coming in here. What do I need? I need the voltage just on the other side. I need my V prime right there this time, don't I? Right? I want to find how much gets across. I need this. So waves coming in, hits the port, some is reflected and some is transmitted. That's the V prime, right? So what do I need to get that, guys? Just give it a shot. What's your gut there? I need the transmission coefficient, don't I? What is the transmission coefficient right here at this port? What would this be? I'm looking for the value of the transmission coefficient here. What is it? That's the transmission coefficient at port 2, which is 1 plus the reflection coefficient at port 2. Do y'all agree? So, what is the reflection coefficient? 1 plus reflection coefficient at port 2 is? Right. So it's really 1 minus 1/5 or 4/5, isn't it? All right, so that means of this voltage V2 prime, the amount, my V prime here, V2, I'll call it V2 prime right there, is actually going to be equal to transmission coefficient of port 2 times V2 plus, or it's equal to 4/5 V2 plus. Then what do I do? Now I got the voltage here, but I need the voltage here, don't I? I need this voltage, what's coming out. So that would be V1 minus, V1, yeah, V1 minus. So how do I get that? Think what that network looks like in terms of just resistors. Can't I replace that transmission line if it's matched with just 50 ohms? So think about it. That means I've got this 50 ohm here, but I already know the V prime across it. Then I've got in series with that 50, right? And then here, the transmission line itself can look like 50. My signal is, I've already got this, I need this, right? I'm calling this, I should call this V1, or call it V prime, just leave it as V prime. And I need this, I need my V1 minus right there. So can you all see that's going to be my V prime, that's across both this one and this one, it's going to be that divided by 2. Can you see that? Because 50 ohms is in series with 50. This 50 doesn't have anything to do with it. You've already got the voltage across it. So, do it here. I have 4/5 V2 plus, and then it's going to be times 1/2 right there, and that would be V1 minus divided by V2 plus. The V2 plus is canceled, and that means my value there is going to be simply 2/5. So now the S parameters would look like this. This is 2/5. And if you want to see if it's a reciprocal network, if I take that times its actual transpose, it doesn't give me the unitary. It's definitely not lossless. But looking at that, just because it's asymmetric, you can tell it's not a symmetric or it's not a reciprocal network. I always think about, if I look this way, it does not look the same as this one. It's simple. The topology is different. Just take a look. Now, if this had a 50 ohm resistor here, then it would be reciprocal. You know what I mean? The minute you see a resistor, it's not lossless. And there are plenty of them. Okay, so that's that problem in a nutshell. Did that help at all? Do it? How about we try one and let you talk to me about how to do it before I go to the next part. I'll go on to this, the actual, what do you call it? Shifting reference planes by adding link. We'll do that in a second. Let's do this 1027. A series capacitor 2 picofarads is inserted in a 50 ohm line at 1 gigahertz. Find the return loss and insertion loss. First, we've got to find the S parameters. So here, we're going to do this. This is 1027. So I have a transmission line here. Z naught equal 50 ohms. I think he said 50. Yeah. And then he has a 2 picofarad capacitor. So he's just going to cut the line and put a 2 picofarad capacitor in series with that. And it's going to be connected back to a 50 ohm line. Now he wants, first I want at least, the S parameter matrix for this. Right, that's the first thing, so I have to get S11, S22, S21, S12 for that. And then he wants the return loss and insertion loss. We'll get both of those in a second. How do I get the S parameter? Start out by saying, how do I get S11? By the way, this is something I will ask you, I'll ask you questions. Let's see. I'm gonna do one quiz, and I'll do it on Monday. And that quiz, instead of doing it on this Friday, I'll do that quiz on Monday, and that will take care of replacing any missed quiz grade, or that one will drop your lowest quiz if you didn't miss any, okay? So I'm not gonna do it this Friday, I'll do it on Monday. That'll be the last day of class, all right? But I'm gonna ask you to please keep up with this, because if you get behind here, you're gonna get clobbered in the next section. You gotta stay up with this. So how do we get S11? What is it by definition? I'll put it down, it's V1 minus over V1 plus, assuming V2 plus is 0. So really just think that this is matched. I'm not gonna keep redrawing. You know, okay, there's nothing coming back at you. Anything that gets through here is not gonna reflect back. So what would that be? Where do you start? I look here, what's the one thing I need for all these? I need Z in right there for port 1, don't I? So the frequency on this one is 1 gig. I need somebody's help on this one. So if we have a frequency of 10 to the 9th hertz, I need really what? I need the impedance of that. What is it? 1 over J omega C, right? So 1 over J omega C is minus J and the value. 1 over 2 pi times 10 to the 9th times 2 times 10 to the minus 12. About 100 ohms. What do you get?
79.6.
Is that right?
I got negative 79.6 J.
Yeah.
Yeah.
79.6 did you say? So this is 79.6 negative. So now what is the input impedance right there on port 1? What would it be? It would be what? That plus 50, wouldn't it? So I'm gonna just write it down. So the input impedance is gonna be minus J 79.1 plus 50. Okay? So what would S11 be, which would be the reflection coefficient, assuming V2 plus equals 0, that would be equal to what? The impedance I'm going into, which is that, which is 50 minus J 79.1. And then it's going to be minus the impedance I came from, which is 50, over the sum of the two, which is which would be 100 minus J 79.1. Now this requires a calculator, but you can see on top, the 50s cancel, don't they? This 50 is canceled by that 50, so it's minus 79 minus J 79.1 over 100 minus J 79.1. And can somebody give that to me in terms of a magnitude and a phase angle? Or real and imaginary part, doesn't matter.
0.623 at an angle 51.5. or negative 51.5, sorry.
degrees, right? Degrees?
Yeah.
Okay. So now we've got S11. Can you wanna take a guess at what S22 is?
That's V2 minus over V2 plus, what do you think?
Same.
Same exact thing. Can you look at that and just see how it's reciprocal? It looks the same from either port. There's no topological change in structure. So that would be 0.623 at an angle of minus 51.5 degrees. Now, how do I get S21? Well, what is that? That S21 by definition is going to be V2 minus over V1 plus. It's a voltage gain, assuming V2 plus is 0, right? So that's the one where I need to find what? I need to find this V prime, right? Just on the other side. You assume V1's coming. You got a V1 plus here, and now I need to find that V prime. And how do I always find V prime? I can say my V prime here is V1, right, plus, and then it's times the transmission coefficient, right? Well, the transmission coefficient would be 1 plus the reflection coefficient of port 1, wouldn't it? Y'all follow me on this? That's the y'all with me? So that's the transmission coefficient. 1 plus the reflection coefficient. I'm doing this for a reason. Then, once I'm here and I have this, now I need to find how much that voltage is actually developed across that 50 ohms. And that would be what? 50, right? Over 50 minus J 79.6, right? Correct? Now here I need your help with calculators. That's the value that goes here for the reflection coefficient. So now I can say, since this is, now it's going to be, this is going to be V2 minus, I can say V2 minus over V1 plus, or S21 will be equal to 1 plus reflection coefficient, 1 plus 0.623.
Is it not 100 minus J 79.6?
Pardon me? What did you say?
Is it not?
Where are you looking?
Right there, at the bottom, it's 50 over 50 minus J 79.6. Shouldn't it be 100 minus J 79.6?
Well, this is, what we're looking here is voltage division, right? Once we have this here, this equivalent resistance is 50 ohms, right?
Yeah.
So what I want to do is find the amount of voltage developed there. That would be 50 over 50 plus this times that.
Yeah, sorry.
No, I mean, it's all right. The question is always,
I wrote the capacitor down as 50 plus that, that's why.
don't ever trust me when it comes to this. Always look suspiciously at me. It's the best way. And that's at 51, minus 51.5, right? I have to take that, then I have to multiply it by 50 over 50 minus J 79.6. You can see how this is going to take you a little time to calculate. All right. Magnitude angle.
0.782 at an angle 38.52.
0.52. Okay. Now, if that's S21, y'all see how that's going to be S12 because it's reciprocal? Y'all follow me? So I'm going to put the S parameters of that thing right here. I'm going to have my S matrix being equal to, and for S11 equals S22 is 0.623 at an angle of minus 51.5 degrees. 0.623 at an angle of minus 51.5 degrees. And then S21 is 782, 0.782 at an angle of 38 point, is it 52?
Yes.
Same up here, 0.782 at an angle of 38.5. So those are the S parameters. Now I'm gonna get the return loss and the insertion loss. The return loss on port 2 is gonna be the return loss at port 1 because it's a reciprocal network. So the return loss on port 1 or 2, I'll just say on port 1, is minus 20 times the log. Here it's absolute value of S11, so 0.632. So can you tell me that? Anybody?
Uh, 4.11.
4.11?
Yes.
And that would be in dB. And this is for the insertion loss, it's 20 times the log of the magnitude of S21 or S12, which is 0.782. And give me that. That's log base 10, remember that, not natural log. If you use MATLAB, LOG on MATLAB is log base E. You gotta put LOG 10 if you want log base 10 in MATLAB. Remember that when you're doing your projects.
2.76.
All right. Does anybody have the solutions up? I'm gonna take a quick picture just to see. Guys, I'm always suspicious. And you can see how there's a lot of room for mistake because those are complex numbers. It's easy with resistors, or easier. Do you have access to them?
Ten 20, sir?
1027.
Oh, sorry, the bottom one, the IL is, 2.14.
2.14?
Yeah, I switched to, I did 728 instead of 72.
2.14 dB. Let's see if I can get this.
That's right, based on the book solutions.
Is it? Okay. That's all I need. All right, next. And I might add that, I think what we're doing right here is, because it's so new to you, it takes a little more time to ingest and really appreciate it. S parameters can get confusing in a heartbeat. We're gonna be doing 3-port and 4-port S parameters, and they can get crazy. I wanted to do shift in the reference plane, but there's a, what do I got, 2 minutes? I won't get through the shift. I'll do that next time. What I'm going to do is, I'm gonna, do you have your books with you? How many have their own books? Do you have your book? Can you? She does. Do you have yours? What I'm gonna do is take a look at the chapter 10 problems for 1 second. There's nothing here. I won't get through the shift in the reference point. On the top of page 611, you're gonna see a figure for figure 1055, and it's used for problem 24. It says, find the scattering parameters for the simple 2-port networks. Now I want you to take a look at this for a second. Do you have a book? You can use mine. When you look at this, just listen to me now. Does everybody have access to the book? When you look at this, take a look at the first one, 2 straight things. Now, if it's 2 straight things and there's a matched load, what would S11 be for that one? Just take a look. Is there any reason for reflection? If you got 2 straight wires, that means Z0 is here, it's coming from Z0. So the input impedance is Z0 to that port 1, same as the impedance you came from. Reflection coefficient is 0. S11 and S22 for the first one, that's A, is 0. Does that make sense to everybody? Now what about the voltage gain? All right, the forward voltage gain is S21. It's V2 minus over V1 plus. If V1 plus comes in and there's no reflection, that is V2 minus, isn't it? So that means the S21 and S12 of that one would be 1. So you would have 0, 0, 1, 1. Y'all follow? All right, this just allows you to get a better feel for these parameters. Now go to the next one. That's B. All right, take a look at that. Is there any way that voltage from port 1 can get to port 2? Immediately you know S21 and S12 are 0. There can't be a forward or reverse voltage gain. Are you with me? Now, when you look at S11 or S22, look at that one carefully. What's the input impedance to port 1 or port 2? Infinite, right? It's an open circuit. You all see that? There's nothing connected. All right, what is the reflection coefficient, which would be S11? It's the impedance you're going into infinity minus the impedance you came from Z0 over that impedance infinity plus Z0. Infinity over infinity is 1. S11 and S22 would be 1 for that one. So it's the opposite. Before, the first one we had was 0, 0, 1, 1. Now it's 1, 1, 0, 0. You can follow me on that? Third one, C. Look at C. What can you tell me about the reflection coefficient of port 1 there, which would be S11? That's a direct short, isn't it? Well, what do you know about that? The impedance you're going into is 0, right? So you would have S11 would be 0 minus Z0 over 0 plus Z0, or minus 1. Do you see that? So S11, the reflection coefficient would be minus 1, S22 would be minus 1. Now what about the transmission, the forward gain or reverse gain? Is there any way any voltage from port 1 can get to port 2? They're both 0, right? So that's minus 1 in the diagonal on S11, S22, minus 1, and zeros on S21 and S12. Okay. What about the final one? D. What do you think about that? What is S11 there? Just think about it. Anybody? What's the reflection coefficient of port 1? It's 1 exactly, right? All right. Now, what's the reflection coefficient of port 2? S22. Minus 1, right? It's a short. You all see that? Now, is there any way, any information from the first terminals for port 1 can get to port 2? Immediately, you know S21 and S12 is 0. Right? I want to do that little exercise with you because that kind of helps you get a flavor, an idea of what you're dealing with. Right? You can take one look at the network and pretty much guess if there is going to be any, what the forward or reverse gains are just by looking at it. I kept you a couple minutes extra. I'll go through a shift and a reference plane. The rest of this we'll get into 3 reports next time. When they give you some homework, please do it. I think I can do it. This makes sense to you? I need to do the problem. It never makes total sense until you go through the problem.